So we're very happy to have Amnon Ta-Shma here from Tel-Aviv University to tell us about the Hermitian trace code. So take it away.
Thank you, ma'am. So I'll tell you what the Hermitian trace code in a few minutes. The goal is to build a good, explicit binary error correcting code, and I won't be able to do that. But I would like to suggest a way how to do. So the most trivial way to construct binary codes is just by taking concatenation. So, the first construction in AGHP is Reed-Solomon concatenated with Hadamard, and then the length is order of k over epsilon squared. So it's k squared over epsilon squared. It's not, the rate is little of one, very little. And then you can try other things. You can try algebraic geometric codes with Hadamard. And this gives k over epsilon.
Epsilon.
What's the distance?
Half minus epsilon.
And k half minus epsilon. And then you can try other things, but there is a lower bound here that whatever you do, it will be omega of k over epsilon cube. And this is if you only use the distance property that you are given about the outer code, then you won't be able to do more than that. There is another way, the second construction in AGHP. So let me tell you what the second construction is. So you want to encode A1 to AK, and it's a binary code. Yeah? They're all in 0, 1. You associate with A polynomial. So the polynomial is x plus 1 raised to the power of A1. A1 is either 0 or 1. It's either you take it or not, and then you multiply by x plus 2. There is no significance to the 1 and 2, just you need distinct elements, and then x plus k to the power of ak. And the only important thing about this polynomial is that it's square free. And then you evaluate it. It's like a Reed-Solomon code. You evaluate it over the whole domain. And then you take, when you evaluate it, you get an element in FQ. So you view it as an element of a large field FQ that has at least k points. And then you evaluate it over n points, so Q is large. And when you evaluate it, you get elements in FQ. And then you take the quadratic character of all functions. So what's this quadratic character? It's a function from FQ to F2. And it's 0 on 0, if A equals 0. And then if A, otherwise, it's 1 if A is a square in the field, and it's minus 1 if it's not a square. And the characteristic is not 2. Half of the elements are squares, half of them are not squares. And so you pull down the element from FQ to F2 in this algebraic way, and that's the code. What? The evaluation points are just all the elements in the field. I see. Okay, is it clear what's the code? Now let's analyze it. So basically, f of A is a polynomial in FQ of x, and it's not a square polynomial. And then veil bound tells us that if we go over all the elements in FQ, we evaluate f on the element, then about half of the elements are quadratic residues and half of them are non-residues. So if we just add up high of f of alpha, so I remind you that it's 1 if it's a square, minus 1 if it's not a square. This is the difference between the number of squares and non-squares. This difference is small. It's smaller than the degree of f times root the number of points. Okay? And because now, in our case, f is not a square, we can apply the theorem. All we need, q is n, let's call it n. We want it to be epsilon n. And then you know it's only, this is, let's call it k, this is like the dimension. And then it's a calculation, and n equals, again, order of k over epsilon squared. Okay, that's the second construction in AGHP. And it's different, right? Because here, well, it looks similar. There is an outer code and an inner operation. But before it was a code, now it's a deterministic function. Okay, I will denote it like Reed-Solomon with the trace function. But it's not really Reed-Solomon because there is this trick here to enforce that we don't have a square. Okay, now, if you don't like this trick, you can actually, what?
So Amnon, just to be sure, you wrote there k over epsilon whole squared, right?
Yes, right, because you see, k times root n is epsilon n. So root n is k over epsilon, and n is k over epsilon squared. Okay? It's not a good code, but it gives an epsilon by space. It's the second construction in AGHP. Okay? Now you can also, you can actually make it closer to Reed-Solomon with the trace.
Question, I think. Maybe I'll ask you. Check this out. Why do you call it the trace code? This is a multiplicative character.
Yes, that's right. Okay, that's right. Okay. Okay. It's a Reed-Solomon plus a character.
Maybe say
Plus a character. Okay, there are additive characters and multiplicative characters. A quadratic residue is a multiplicative character. The trace function is a linear character. But basically, they all behave the same. There is what?
I want to say something of what is AGHP?
What is AGHP? Okay, AGHP is Alon, Goldreich, Hastad, Palata. It's a paper from '92. It's one of the first papers to Noor and Noor suggested epsilon biospaces, and they gave constructions for epsilon biospaces. And, okay. Okay, good. Okay, so now let's make it closer. Let's really, what?
So the polynomial we care about is some special polynomial depending on the k-length binary vector.
Sorry, say it.
So the polynomials we wanted to evaluate is the special polynomials with that structure depending on the binary k-length vector.
These are special polynomials. It's a linear space of polynomials
Okay.
that are all square free.
Okay.
Okay?
It's not a linear code.
It's a linear code, right? It's not a linear space of polynomials, but it's a linear code. Okay, for every a you associate f of a, and there is an element f of a plus b.
The product of the code.
No, let's not think of it. It gives a linear code, but let us straighten up this issue. Let's do it in a different way, but let's do the same thing. Okay? Okay. So I would like really to do Reed-Solomon plus trace. Okay. So what is this trace? So suppose Q now is a power of 2. We'll take an additive character. The additive character would be, trace of x is sum over x to the power of 2 to the i. I goes from 0 to n minus 1. That's trace of x. And it's an additive character, and it behaves very similarly to multiplicative characters. In particular, if f is spanned, okay, there is another Weil bound that if f belongs to the span of x to the I, where I is odd, then again, the sum of their own elements in FQ, f of alpha, and then on top of that we take trace, and then, okay, let's assume that the trace, instead of giving you 0 and 1, gives you 1 and minus 1. Okay, so the difference between the number of ones and the number of zeros is at most, so formally this is false, but you understand, is again an order of d times, maybe it's exactly, it's at most d times square root q. What? Where d is the degree of f. Okay, so now if you want to build a code, it's exactly the same construction, but I think it's really, it clarifies the linearity and everything. So we start with some f, which is in that span. It only slightly reduces the dimension. It's not really important. And then you, like Reed-Solomon code, we evaluate it over everything, and we take the trace. So the code word of f is trace of f alpha 1 up to trace of f alpha q. And then it's exactly the same calculation, and it gives you a construction, a code with length, which is order k of epsilon square, right? So this is has a feeling of being in the 90s, right? So we know so much more than that, right? But let's start with the basics. Okay, so now because we know so much, I want to ask you a simple question. Okay, so the question, here's the question. What happens, by the way, this is called the trace code, right? And there is a lot of literature about trace codes. Okay, so here's the question. What happens if we replace the outer code with another good AG code? Okay, so that's the question. It's really simple, right? There is a simple construction. It uses a different idea, and you know, it's not so easy to analyze this, but it's a very natural question, right? So, for example, when we did concatenation, it was much better to concatenate, instead of concatenating with Reed-Solomon, to concatenate with an AG code. Okay? So this is the question. This is what I would like to discuss. Okay? Is it clear what we want to do? Okay. Now, I will talk today about the Hermitian trace code. So we will replace Reed-Solomon with the Hermitian code. Okay, so let me tell you what's the Hermitian code. Okay. So, okay. So the Hermitian code is an evaluation code, like all algebraic codes. There is a set of evaluation points. What are these evaluation points? So we take Q to be p squared. P is some prime power, or if you want, it's a prime, it doesn't matter. And Q is p squared. And the evaluation points are all the points A, B in FQ cos FQ, such that trace of B equals norm of A. So trace is from FQ to FP. And so let's write it explicitly. It means that B to the P plus B equals A to the P plus 1. Okay? So these are the rational points of a curve. And these are the evaluation points. Just let's see that we are together. The size of H, what is the size of H? Yeah, you know, P cube. Why? Because for every element A, the norm of A is in Fp, and then there are P solutions. Okay? So this is the set of evaluation points. And what are the evaluation polynomials? Evaluation polynomials are all the polynomials in X and Y such that the degree of P is small. So in a sense, artificially, it looks like Reed-Muller in 2 variables, but it's really a one-dimensional object because it really works on a curve, which is a one-dimensional object. It's more similar to Reed-Solomon than to Reed-Muller. Okay, so is it clear what's the code? And now let's analyze it. The length is P cubed. The alphabet is P squared. When we evaluate, we get elements in FQ. The dimension we'll write in a minute. And what's the distance? So if F is in FQ xy, and it's not the zero polynomial, then the number of zeros that F can have on H is really the intersection of the zeros of F and the zeros of the curve, right? So it's really all elements alpha in FQ times FQ, such that phi of alpha is 0. Phi of alpha is this equation. And f of alpha is 0. And this is an irreducible polynomial, that's a fact. And then by Bezout theorem, the number of elements in this intersection is at most the degree of phi times the degree of f. See, so that's easy. So the number of zeros is at most d times p plus 1. So the distance is at least the length minus that. Okay? It's really easy. And what's the dimension? Then
P is less than P.
what?
The degree is less than P.
The degree of f is d.
And we've taken it to be less than P.
No, not necessarily, no. No, actually, d can be up to p squared, about p squared, and then you would get a code with a constant rate, and in fact, it would be optimal to the point. Right? Hermitian codes are optimal to the constant.
There should be common factors, right? Like
What?
Like phi should not divide phi.
Phi is irreducible, absolutely irreducible. Okay?
Well, I think if the degree of f is more than p plus 1, phi might divide f, so you have to be careful.
So it's not all, so it's not all polynomials evaluated. It's just with some degree restriction maybe, so that
Actually, the P you choose is something like not the polynomial or two-variable polynomial ring, but something like more and more.
So I think f should come from the function field. So you take the modulo phi anyway. But you're right that if you look at it as coming from a polynomial ring, then you should. That's right. So I mean, if you really want to define it, then f should come from a function field. Okay. Okay. Now what's the dimension? Well, if d is smaller than p, then the elements x to y, y to the j, where I is smaller than j is smaller than p plus 1 are all independent. And therefore the dimension is about, and then the dimension is about t squared over 2. I mean, all pairs give you are independent. And if the dimension is above P, then the dimension is the degree of the divisor minus the genus, which is P squared over 2. But if you didn't understand that sentence, you can just ignore it. Because we don't know to analyze the case that D is larger than P, we only know to analyze the case that D is smaller than P, so this is our case. But just for general knowledge, the Hermitian code is as good as it can be. Okay? So that's the Hermitian code.
What do you mean we don't know how to analyze it? Someone.
Oh, okay, I'm going to prove something and not just tell you a story. Okay, I'm not going to prove it, I'm going to tell you about a proof. Okay, so, okay. So now let's look, we are interested in what? We are interested in sum over all alpha in H. These are all the evaluation points. The quadratic residue of f of alpha. Okay, I'm working with a multiplicative character. It's not really important, but I mean, I think it's easier. Okay, so we want to bound that, right? Now, veil bound works over FQ. There is no guarantee that it is also working over the Hermitian curve, right? So now let me offer you some possibilities about what the true answer is. So there is some bias function. Now, of course, it's possible that it's completely biased. It's possible that the bias is n and then we lose, but we actually prove that this is not the case. Now, it's also possible. What would you say the bias is? I think it's most natural to expect that it's some multiple of root n. Root n is the number of points that we are summing. And in a random process, we expect a root n deviation. Now, I mean, before we saw a bound of d times root n, but it's not the same d, because in one dimension, the degree is also the number of zeros. And I think it's most natural to expect that, that this root n is multiplied by the number of zeros of the function, which is also the number of poles of the function. So one could, and this is really the number of zeros and poles. In a minute, I'll tell you why. So I think this is the most natural thing to expect. Okay, and let me tell you why. What?
So this is for the degree polynomial, right? Over
yes, for bias for a degree D polynomial over the Hermitian field. Okay. Okay. Why? Because, for example, look at the polynomial x. Its degree as a polynomial is 1, but how many zeros does it have? So when x is 0, y to the p plus y equals 0, and then there are p solutions, right? So the number of zeros is p. And similarly, if you look at y, when y is 0, then x is 0, so it looks as if there is only one solution, but really you get that x to the power of p plus 1 is 0, so you get p plus 1 solutions. You get one solution with multiplicity p plus 1, and you can actually make it precise. So this is really, or if you want to be really rigorous, this is what you would expect, I think. And in fact, we prove that this is also not the case, because we prove that the bias is order of that, is at most the order of that. Now, this is not a natural thing. I have no explanation to that. I have no idea. I mean, maybe Swastik knows. No. And it's also possible, I mean, Swastik wrote that it might be the case that the bias is d times p root n. Okay? Okay, this is also, I mean, if you think, so, d times root n. Right? Okay, good. Now, what does it all mean, right? Let's assume maybe it's less, right? But in a minute we'll see that it can't be less. Okay, so what does it all mean in terms of codes, right? What kind of codes do you get? So you can do the calculation because D is really about K squared, and you just do the calculation. Do the calculation, you get blah, blah. I don't know, K to 6 over epsilon. I think it's something like that. I'm not sure. But if you look at that, you get K over epsilon squared. Okay, so now we are going to prove that. Okay, so let me tell you this. People looked at character sums over the Hermitian function field before us. There are two ways to prove that, either with algebraic geometric arguments, and then I think Swastik managed to prove some constant bias, right? And then there is also another way to prove it with Stepanov. I'll tell you more about it in a minute. But they didn't get much. So even that is more than what people knew before. And this is, I think, a surprise. And this, we don't know, but it's possible. And if it's true, then you get a code, a binary code, meeting the Gilbert-Varsham bound up to constants.
What's the intuition?
What?
The left order of the intuition for the P appearing there.
Yes, I have an intuition for that, but that's obviously wrong. Okay?
No, but that depends on P, I mean.
What?
P is the same in the intuition and in the proof.
Well, why should it depend on T?
Why shouldn't it?
Why shouldn't it depend on P?
Given that you have like P poles every.
Okay, well, it does depend on P, right? N is P cubed, right? But the question is, okay, I don't have an intuition for that. And the reason I don't have an intuition is that the proof I know is using Stepanov. It's a computer science proof. It's easy, it's working, it's great. You can actually work with it, but it doesn't tell you anything meaningful about the object you study. Okay, that's my feeling. Okay, so I talked with some good people studying AG codes, and they talked over my head in a ping pong, but I didn't understand the word for an hour and a half. And then at the end, they told me, this is the answer. But I wanted them to actually write it down or tell me why. And they said it's too complicated and it doesn't work that time. So I'm not sure. I have no idea how much weight you should give to that. And I have no intuition about it. Okay? And I have no intuition about Stepanov. I can only explain you what he does, but I have no intuition about it. And but I just a word of warning, that would be a code close to the Gilbert-Varsham bound, but with dimension p squared out of length, which is p cubed. Right? So it won't be a constant rate or good rate. But on the other hand, it's much better than what we know today. Today, we know only codes on the very far extremes that are better than the Gilbert-Varsham bound. And this is not an extreme code. Okay? Okay. For example, both Hadamard and Hamming are better than the Gilbert-Varsham bound, but they are really extreme. Okay? Okay, so this is just to make you interested in that and maybe also studying that. And okay, but now I'll tell you about the proof. So the theorem is that if f is not a square, so f is in the Hermitian function field, so it's fqxy modulo phi. Okay. And f is not a square. Then sum over all alpha in H of the quadratic residue of f of alpha is at most order would be times p. Okay, so that's the claim. Okay, now I already told you that we are going to prove it with the Stepanov bound. So let me tell you about the way Stepanov proved Weil bounds in 1970. Okay, so the claim he was trying to prove is the following bound. I wrote it before. If f in fqx is not a square, then sum over alpha is order of d root q. Stepanov proved it with some constant factor here. The correct claim is without with one. Okay, so that's the claim. And then he said, a very simple idea. He actually proved it, you know how? He proved it with a polynomial method. Okay, so he said, okay, what is really the question? The question is, how large the set of all elements x such that character of f of x is 1 and x is in fq. So equivalently, it's like saying that f of x to the power of q minus 1 over 2 should be 1, and x to the q should equal x. So this is really a variety. It's a closed algebraic set. It's a variety. It's very simple. It's very, it's not a set just from the street. It's something with dignity. It has structure. And we want a polynomial. We look for a polynomial. We look for a polynomial such that q of a is 0. In fact, we want something more. We want that the multiplicity of q on every element in A is at least t. Okay, what's the multiplicity? It means that also the derivatives of q vanish on A. Okay? Now, what Stepanov said, okay, Stepanov said that he can prove that there is a low degree polynomial q that vanishes with high multiplicity over A, and therefore you can conclude that the size of A is at most the degree of q divided by t. That's the polynomial method, right? But there is a twist to it, because, I think we now automatically, if I ask you to find a polynomial that vanishes over a set, what would you do? You write an equation for every element in A, or maybe several equations if you want high multiplicity, and then have enough degrees of freedom to accommodate all the constraints, right? If you do that, you fail, because A is, it doesn't work. It gives you nothing. But the thing is that A is really, the set A has structure. It's an algebraic set. So Stepanov said, let's look, we will look for Q in the following set. Fx to the t, that looks mysterious. In a minute, I'll explain you why. And the span of the elements, x to the I, x to the qj, and fx to the power of q minus 1 over 2 to the power of k. Now, I and j are bounded by something, and k is either 0 or 1. Okay? And Stepanov proved that if f is not a square function, if it's a square function, you see that it's not good. You get f of x to the power of q minus 1, and here you have x to the q. It's not good. But if f is not a square function, then he proved that if A and B are chosen appropriately, then all these elements are independent. You have many degrees of freedom. What?
What's the exponent of the second x to the power?
It's important. It's x to the power of q times j. Okay, and why is that? The thing is that now suppose we want to impose constraints such that q of A is 0. Then this means we have q is sum over alpha I and these elements, x to the I1, x to the q times I2, fx to the power of q minus 1 over 2 times I3. Okay? And then we have fx to the t here. But because we know we are only interested in elements that come from a variety, so we know, right, because for every A in A, we know that A to the q is A, and f of A to the power of q minus 1 over 2 is 1, right? So these things, this is actually x to the I2, and this is actually 1. So this whole thing lives in a very low dimensional space of dimension only A plus B. So here we have many degrees of freedom, and every constraint is just few constraints. Now, just notice that it's different. We don't care how large A is. We are not working per element of A. We are just working globally over the variety, and we are forcing that q of A is 0. And we do the same for the derivatives. When you take a derivative of that, you get f of x to the power of q minus 1 over 2 minus 1. So that one doesn't cancel out with that. And because of that, we need, in a way, to fill in the whole. So we take it.
So I'm probably missing something. Maybe it's the derivatives. But if f of x to the q minus 1 over 2 is 1 throughout A, is it really more degrees of freedom? Like, because that's a function, it's the same function.
Okay, so that's the magic of it, right? So this is a very large space of polynomials, and they're all different. But when you evaluate them over a variety, there is a collapse that is happening, right? And actually, this collapse is frightening. It looks as if you should be able to prove the impossible, right? Because there are so few constraints. But when you do the calculation, you see that math is taking care of itself and everything is fine. You don't prove a contradiction. Okay, but so this is really the magic of it, right? When you try to use a polynomial method over varieties, you can do it in a much cheaper way.
And it's important to use multiplicities, otherwise you don't get anything.
Yes, it's important to use multiplicities, otherwise you don't get the result. And all the parameters have to be very carefully chosen. But I will save you the parameters, because after that, it's only calculations. Calculations and choosing the right parameters, and it's quite a lot of work. You can read about it in several places. Swastik has lecture notes about it, and it appears in the book of Chen, Kayal, and Vigdazon. They have a chapter on it. It appears in many places. It's not, I mean, there are many calculations, but this is really the idea behind the construction.
So can I bother you again? I feel like I'm missing the whole point. So take the time. So for example, if you do AG codes, for example, then you do count degrees of freedom according to the Riemann-Roch space. So if functions are the same on the curve, they are 1, not many.
In a minute, we'll do it over an AG code. Okay? So can you postpone the question? Okay. And how much time do I have?
When did we start? Take 5-10 minutes. Take 5 to 10 minutes.
5 to 10 minutes. Wow, that's a lot. Okay, good. So I have time to say what I want. Okay, good. Okay. So now we want to generalize it to the Hermitian curve. Now let me tell you a basic way of doing that, because it requires less algebra, and I think it's It's more explicit. So now when we walk over the Hermitian curve, then we have x and y and f of xy. And we know that we are looking for rational solutions. So this should be 2. We also should be over the curve. So this should also be 2. And we want the output to be quadratic residues. So this should also be 2. Right? So now we have to choose some basis. So you can choose the following basis: x to the I, y to the j plus k times p plus L times q times f of xy of q minus 1 over 2 times k. As before, k is either 0 or 1. And then you need to impose, that I, j, k, and L are smaller than something. And it actually works. You can do the calculations. When you have many degrees of freedom, these things are independent if f has the right conditions. Maybe it's not exactly that it's square free, but whatever. If f is some easy to say, obeys something easy to say, then all these things are independent. You have many degrees of freedom, and when you evaluate it over a variety, then things collapse, and then you just need to choose parameters and do the calculations, and it works. Okay, so that's one way of doing it. But I really didn't say something very important. We need Q to vanish with high multiplicity, and you didn't ask me what's exactly the definition of the derivative in the function field. Okay, so I think that's really something, that's not really a matter of parameters, that's really something fundamental. Let's give it a moment of thought. Okay, so we all know how to differentiate in the polynomial ring. But how do you differentiate in a function field? So suppose we have this Hermitian function field, and we want to, let's say, to derive by x. So if we have polynomials in x, we know how to derive by x. It's I, x to the I. Right? But what's the derivative of y with respect to x? Okay. And think of the curve as going, it doesn't go, it's a polynomial equation, right? It goes, well, over a finite field. It's really crazy. So what is the derivative of y with respect to x? But there is an easy answer to that. Because y to the p plus y is x to the p plus 1. So there's only one way it can be. Y to the p plus y divided by x should be p plus 1 to the times x to the p. And p plus 1 is 1, so this is x to the p. Now, the derivative should be linear. So it's y to the p divided by x plus y divided by x. And this thing, by the chain rule, should be p times y to the p minus 1 times y derived by x. And this is a 0. So the conclusion is that the derivative of y with respect to x is x to the p. And in fact, you can define with algebraic axioms what a derivative should obey, and then you can prove that there is only one way to derive according to a variable, and you can also talk about the vector space of all derivatives, and it's one-dimensional, and there is a lot of mathematics. Okay, so is it clear? Now, I want you to notice one thing, that y, we said before that y has p plus 1 zeros. but the derivative of y with respect to x as p squared zeros, right? So the conclusion is that the derivative of y with respect to x is much more complex than y. We are used in the polynomial ring that when we derive, we get a simpler function. And if we derive enough, we get a constant and then it vanishes. But in fact, this is not even true for quotients. If you take f over g, then you have divided by g squared, and you see that actually you get more zeros, more poles. And it's completely not true in an algebraic function field. In an algebraic function field, usually the derivative is much more complex than the original function. Okay? Now, and that, of course, influences all the parameters, but they work out. Now, there is a more structured way. I'll take 4 minutes, okay? A more structured way to prove the same thing, which is to really work with correct algebraic geometry notions, like extension fields and everything, and genus and everything in places. And then you don't have to choose a specific basis, right? Things become more abstract and general and in a way, but the price you pay for that is that they are also less explicit. If you want to claim that you have many degrees of freedom, you use the Riemann-Roch theorem that tells you that there is a large basis, but it's not explicit. And when you try, you need to differentiate it. It's not clear what are the differentials, and they create holes all over the place. It's not clear where the holes are, right? It's very hard to control it. So then we have a lemma that I want to tell you, which actually tells you that the situation is not as bad as it looks. So the lemma says that if f over k is a function field, like, for example, in the Hermitian function field, this is fq, and this is fxy, where trace of y is norm of x. And if x is separating means, this is a one-dimensional, this is as transcendence degree 1. Like in the polynomial ring, we have one variable that is transcendent. And x is separating if when we add to the base field, we add x, we get something that is a finite extension. Okay? And if x is separating and p is a degree 1 place, it's like a point on the curve. Then there exists some element that depends only on x and p, but it's really x. One element w, omega, such that for any function g in L of p, this means that g has poles only at p. If we look at the derivative of g with respect to x, and we might be worried that the poles are scattered all over the place and they depend on g, and who knows what happens. And it's true that who knows what happens, but if we multiply it by omega, what? Only one?
One pole.
No. This is actually, okay, this is a union over all t. Okay, it has poles only at the place p. Okay, then omega times the derivative of g by x also belongs to L of p. It means that we managed to fill in all the holes that were created elsewhere, and also the number, do you see that? The number of the number of poles or zeros, it doesn't matter, of omega times G prime, G derivative, is at most the number of poles of the derivative of G plus the penalty. The penalty is 3 times the genus plus something that depends on X. So we can choose X so that it's small, but the penalty is really basically 3 times the genus. I think it can probably be improved to twice the genus, and twice the genus is probably the correct answer. But the thing is that even if we take a basis, but we don't know exactly what the basis is, and we differentiate it, we might get poles all over the place. We can just fill them in like before with one single element, and then the same argument works. Okay? So that's it.
One quick question.
So there is this extension of this construction. You can add algebraic variables, and then ultimately you get the tower of those curves, and you get very good codes. Can you maybe try, for the next step, you add on more variable and see what happens?
Yeah. Okay. So we actually can prove it for a larger class of algebraic geometric codes. For example, we can also prove it for the Hermitian tower for any constant number of levels.
Garcia-Stichtenot, right?
What? Garcia-Stichtenot, first of all, yeah, it's not a tower over the Hermitian curve, right? It's a slightly modified curve.
Yes.
And also, the length, the depth of the tower is going to infinity, right? And we only managed to prove it for constant depth, right? But we only started the work on it, and I think we are not mathematicians, and actually I think that there should be better answers. Okay, and I'm really intrigued by that possibility that maybe it can give a good binary code. Okay.
Maybe in the interest of time, let's take further questions offline, and let's thank Amnon again.